For this problem, we have two problems. The first one is we are given four forces F1, F2, 6 kN and 12 kN force applied on the XZ plane with XZ coordinates. So let's write this down. This is our Z-axis and this is our S-axis. And our axis acting perpendicular. Let's say it's right here. We have force F1, which is acting at the coordinates of 22 in the X direction and 0 in the Z direction. So let's say it's right here. And we have force F2 acting in the coordinates 0 in the X direction and 20 units in the Z direction. So let's say it's right here. And then we have force 6 kN acting in the coordinates 26 in the X direction and 20 units in the Z direction. And also we have the 12 kN force acting in the coordinates 6 units in the X direction and 8 units in the Z direction. So we have 12 kN with coordinates 6, 8. And it is asking us to find the value of F1 if the resultant is located at the coordinates 12 units in the X direction and 10 units in the Z direction. So let's say it's right here. Now to solve this problem, what we can do is take summation of moments in the Z direction equal to the moment induced by the resultant in the Z axis. So the moment induced by R along the Z axis about the Z axis, that is equal to R times 12. That is the distance of the moment arm from the Z axis, which is equal to 12. So summation moment Z, we have a force 1 F1 multiplied with moment arm distance of 22 plus F2 multiplied by the moment arm distance of 0 plus 12 kN times 6 plus this is 6 kN multiplied by 26 equal to the resultant moment along the about the Z axis. That is R times 12. And then take summation moment along the about the x-axis equal to the moment induced by the resultant about the x-axis. That is the resultant times the moment arm distance of 10. So we have F1 times the moment arm distance along from the x-axis is equal to 0 plus F2 times 20 plus 12 kN force times 8 plus 6 kN force times the moment arm distance of 20 equal to R times 10. And lastly, for our last equation, we take summation force along the y-axis. That is equal to, and that's not equal to 0, is equal to the resultant force acting in the along the y direction. So we have F1 plus F2 plus 6 kN plus 12 kN equal to the resultant R. Okay, so we can erase this and focus on our equations. So here we have 3 equations with 3 unknown forces. So let us rearrange these equations. For the first equation, we have 22 F1 plus 0 on F2 and then minus 12 times R equal to, this will be constants to the right, this is negative 12 times 6 minus 6 times 26. For the second equation, we have 0 times F1 plus 20 times F2, and then let's move the resultant to the left side. We get negative 10 times R equal to negative 12 times 8 minus 6 times 20. And for our last equation, we have F1 plus F2 minus R equal to negative 6 minus 12. So to solve these 3 equations with 3 unknowns, we can use our calculator to solve these 3 simultaneous equations. Go to mode 5, 2. So here, our A variable represents the force F1, and for B, this represents our force F2, and for C, this represents our resultant force R, and for D, that represents our constants. So let's plug in the coefficients of the variables. We have f1 having a coefficient of 22, f2 has 0, and r has negative 12. And for the constant, that is negative 12 times 6 minus 6 times 26. And for the second equation, f1 has 0, f2 has 20, and r has negative 10. And the constant, that's negative 12 times 8 minus 6 times 20. And for the last equation, we have f1, f2, negative r equal to negative 6 minus 12. So the value for f1 represented as x is equal to 37.6. And for f2 represented as y equal to 24 kilonewton. And for the resultant, its value is equal to 69.6 kilonewton. So the answer for this problem, it is only asking for the value of f1 that is equal to 27.6 kilonewton, which is letter C. For this second problem, we have a force F applied from point 3, 4, 7 through point 1, 2, 6. So let's draw the figure. So we have our z-axis, the x-axis, and the y-axis. So let's plot the points of the coordinates. So force F is applied from point 3 units in the x direction. So let's say it's right here, and then 4 units in the y direction, and 7 units in the z direction. So let's say it's located here. And it goes through point 1 units in the x direction, 2 units in the y direction, and 6 units in the z direction. So let's say it's located right here. So connecting the points, we have our force Z going in this direction, as shown. Now to solve for the angle of the resultant, we need to solve for the components of the force vector. So we have a component acting along the x direction, let's call this fx, and a component acting along the y direction, we call this fy, and in the z direction, we call this fz. So to solve for these components, we need to solve for the length of the force vector. So to do this, to solve for the length acting in the x, y, and z direction, we subtract the components, the coordinates going from the head to the tail of the vector. So for the length, for the x component of the length, we subtract the x coordinate from the head, that is 1, minus the x coordinate of the tail, that is 3, which is equal to -2. We do the same for Ly, that is 2 minus 4 equal to -2. And for Lz, that is 6 minus 7 equal to -1. So then, by using the Pythagorean theorem, that's equal to the square root of Lx squared plus Ly squared plus Lz squared. So the length L is equal to -2 squared plus -2 squared plus -1 squared. So L is equal to 2 squared, that's 4, plus 4 plus 1 equal to square root of 9. So length L is equal to 3 units. Okay, now that we have solved for L, we can now proceed solving for the resultant from the z-axis. Solving for the angle of the resultant from the z-axis, we only need to solve for the z component of the force. So by using a ratio proportion, Fz, ratio to the total net force F, is equal to the length of the component along the z-axis over the overall length. So Fz is equal to F times Lz divided by L. That is equal to 80 kilonewton times Lz, that's equal to -1 divided by 3, which is equal to negative 26 point. So the negative sign here indicates that Z is acting opposite to the positive Z-axis, so it's going downwards. And to solve for the angle between the force F to the Z-axis, we take the cosine theta equal to the adjacent side, that is Fz, divided by the hypotenuse, that is F. So theta is equal to r cos of Fc, that is equal to negative 1 divided by total force F. Now Fc is equal to 26.67 divided by F. Solving for theta, we get r cos of negative 26.67 divided by 80. We get 109.47 degrees. And that's our final answer. That's letter D.